We saw that the amplitude of probability for a system to move from one event to another can be written as a path integral involving the action. Therefore, all the physics of the system, its mass, its dynamics, its spin, is encoded in the action itself. And of course, the action also encodes the physical laws like translational invariance, Lorentz invariance for relativistic system, Galilean invariance for non-relativistic systems, etc. As our goal is to merge quantum mechanics with special relativity, we need to enforce Lorentz invariance in the action itself to ensure that the physical laws are the same whatever the inertial frame of reference. Therefore, the action needs to be a Lorentz invariant which takes the same value in any inertial frame of reference. Because the action is just a number, this is called a Lorentz scalar. We also know that the action can be expressed as a time integral of a Lagrangian, which is itself a function of the dynamical variable and its time derivatives. The time derivative is important to encode the dynamics of the system to describe how it moves, how it evolves. The simplest object which contains a time derivative is the derivative operator del mu. The latter contains a Lorentz index mu. So if I take the derivative of a function of space-time f, I get a quantity which is not invariant under Lorentz transformation, taking the system from one inertial frame to another, but instead it transforms as a Lorentz vector. To transform a Lorentz 4 vector, we need a 4x4 matrix. Lambda cannot be any 4x4 matrix. It is constrained by the fact that the metric is the same in any inertial frame. It is a Lorentz invariant. The metric has two Lorentz indices. Therefore, it is a rank 2 Lorentz tensor and requires two lambda matrices in order to be transformed from one inertial frame to another. This property is one way to define Lorentz transformations. Examples of Lorentz transformation which obey this definition are boost and rotation. Let's take the example of a boost along the x-axis. We can then write the matrix lambda used to transform Lorentz vector from S to S dash, where gamma is a Lorentz factor. In the case of a rotation around the z-axis, we have So how do we construct a Lorentz scalar when we have Lorentz vectors? The answer is to contract the indices, where we use the same Lorentz index for both vectors, one up and one lowered. So let's apply a Lorentz transformation to both vectors in order to verify that this quantity is indeed a Lorentz scalar. We have used the definition of the inner product between Lorentz vector, which involves the metric, and then we have used the definition for the Lorentz transformation of a 4 vector. We now recognize the Lorentz transformation of the metric, but the metric is invariant. Again, this is a definition of an inner product. Remember that with Einstein convention, repeated indices are summed over, therefore these are dummy indices and I can relabel them. We see that the inner product of A and B, which is just a number, is invariant under Lorentz transformation. It is then a Lorentz scalar. In building our action, we will then need to make sure that every Lorentz index is contracted. Note that when I transform the vectors, I introduce new Greek letters because these are different dummy variables. At the end, I have a sum over mu, a sum over nu, a sum over alpha, a sum over beta. If I used nu instead of alpha, for instance, that would be a different quantity.